Hello everyone, my name is Neha and this is the 7th lecture on electronic circuits. In this lecture, I'm going to teach you oscillator circuits. So let's get started. Introduction to oscillators. Oscillators, they are electronic circuits that generate an output signal without the necessity of an input signal. So basically, the oscillators, they accept the DC voltage and they generate the periodic AC signal of the desired frequency, and it can generate the frequencies from few hertz to even in gigahertz. And the output from the oscillator, the signal which it contains, it can be sinusoidal, it can be non-sinusoidal. So non-sinusoidal signals are like your square wave, triangular wave, sawtooth wave, etc. So all these points you see are the same. So let's quickly read here. The output voltage can be either sinusoidal or non-sinusoidal depending upon the type of oscillator. So there are two types of oscillator: linear oscillator and non-linear oscillator. In non-linear oscillator, you can generate waveforms like the triangular waves, sawtooth or square waves, which uses the non-linear devices like your inverter, comparator, etc. And in the linear oscillator, you have like a sinusoidal signal coming out in a periodic way. And the last point says different types of oscillator produces various types of waveform is the same thing. Now let's see next. So this is a block diagram, and at the center you see this is an oscillator which is accepting DC supply voltage, and at the output you can see what these different types of waveforms can be generated. The first one is your sine wave, second one is your square wave, and this is the sawtooth waveform, and it can also generate the triangular waveform. So these are the three common types of output waveform which an oscillator generates. Now, what are the applications of oscillators? So oscillators, they are used to generate signals. Example, used as a local oscillator to transform the radio frequency signals to the IF frequency signal. IF is basically intermediate frequency signals in a receiver. And they are used to generate RF carrier in a transmitter, and used to generate clocks in digital systems, used as a sweep circuit in TV sets and in CRO. And there are many other applications. For example, in daily use, you might have seen in the laptops, like you might have not seen in the laptops, but it's inside the circuitry. If you get a chance to open it up, then you'll see there are lots of oscillators involved in the circuitry of the laptop. And then in your smartphone processors, you can find the oscillators, and they are used for generating the clock signals. And as I said, they are used in radio. They can be used in mobile receivers for generating the local carrier frequency. And they can be even used in the signal generators, for example, the equipments which you use in the lab to test the circuits. So CRO, as it's written here, in that also you have an oscillator. In function generator also, it converts a signal into different types of waveform. So that also has the oscillator in it. Okay, now let's move on to the next slide, and this slide talks about the principle of oscillator. And the oscillator consists of amplifier, and then there is a feedback network, which is this beta. So we have two important elements here, the amplifier and the frequency selective feedback network. And always remember, the feedback which we are providing in the oscillator is a positive feedback. So it's written also here, it's a positive feedback, and through this symbol also you can basically determine whether it is a positive feedback or a negative feedback. So in the oscillators, we provide the positive feedback. And then this frequency selective circuit, you can use a resonant circuit also to provide the frequency selective output. We will see that what kind of circuits we can use later in this lecture. Now let's see what will happen if the phase shift uh, is introduced by this amplifier. And let's assume if your feedback circuit is 0 at that time when there is some phase shift is provided through this amplifier, then what we are going to get here, in that case the since the feedback signal is 0, then we can say that this feedback signal will be in phase with the input signal. So you understand, when the feedback circuit is 0, in that case you can say the feedback signal will be in phase with the input signal. Now let's imagine if the feedback signal is being added to, there is some already signal here is being added to the input, and at the same time the input signal, which is this Vs, is removed from the circuit. So if it is removed from the circuit, then what is happening? You are providing Vf input, Vf feedback, which will act as your input for this amplifier. And that's what happens in the oscillator. Like, you provide the input signal, and once the oscillation it starts, so the input is basically is basically sent from this feedback network to the amplifier circuit, and then it keeps on moving until it is being stopped. Okay, now let's quickly read here. For sinusoidal input is connected linear because the output is approximately sinusoidal. A linear oscillator contains a frequency selection feedback network, an amplifier to maintain the loop gain at unity. So loop gain is nothing, it is the multiplication of A and beta. When this A beta is equals to 1, so A is the amplifier and beta is your feedback network. So when the multiplication of these two is equals to 1, then you are going to get the sustained oscillation. We are going to see that in the next coming slide. So here you see the basic linear oscillator circuit, which has the amplifier and frequency selective feedback network, and then this summation, and the output voltage is here. Now we are going to write down the equation from this circuit. So let's first see the equation for output voltage. V0 is your output voltage, and then this V0 should be equal to the input voltage and some gain A. Okay, so that's what it is written here. V0 is equals to AVE, where A is the gain and V is the input voltage. Okay, and what is VE? So if you notice here, VE we are getting here from these two signals. So if we add the VS is the input signal which is going into this, and then we have the feedback voltage which is going here. So when these two voltages are added, then we have this VE voltage. And that's what it is written here. V is equals to Vs plus Vf, and where the Vf is what? So you have to see what is this Vf voltage stands for. So this Vf voltage is basically equals to the output voltage, which is coming from here, this V0, and some gain which this feedback network is providing. So that is beta V0, and that's what you see here. Now the next step is, if you put the value of this beta V0 here in this first equation, so if you put the value here, beta V0, and then when you open it up, this bracket, when you open it up, then what will you have? You will have A Vs plus A beta V0, right? So I'll quickly maybe write down here, pen. So you will have something like this: V0 is equals to A Vs plus A beta and then V0. Right now, what we are trying to do, we are trying to find the relationship between the output voltage and input voltage. So output voltage is this one, input voltage is this one. So by that we will know the relationship between these two voltages. So what we are going to do, we are going to take this portion to this side and see what will happen. So we will have V0 common, and then we will have something like this 1. So this is your V0, and minus A beta is equals to A Vs, right? And then so finally what you're going to get is V naught upon Vs, which is equals to A 1 minus A beta. So that's the same equation you see here. Okay, so but I just showed you the steps how to get to this particular step, and this is a very important equation. Okay, so if Vs, it says, let's read here, if Vs is equals to 0, the only way that V naught can be non-zero is that the loop gain is equals to 1. And when this loop gain is equals to 1, that is the condition we want to achieve. That is the condition of a sustained oscillation. So we are going to see that next. But yeah, this condition when A beta is equals to 1, that condition is basically obtained from Barkhausen. So this was some scientist who has invented this, and that's why it is called Barkhausen criterion. Now moving on to the next slide. So in this slide, we see different types of oscillation, and these are the 3 different conditions when A beta is less than 1, when A beta is greater than 1, when A beta is equals to 1. So you can see that when you have A beta less than 1, then this kind of oscillation you will get, and you see that it is the oscillation is of higher amplitude in the beginning, and then it diminishes. And whereas in the second one, when A beta is when this is greater than 1, then initially you have the low oscillation and then it increases. So these two are not your sustained oscillation. So you get the sustained oscillation only when you have your A beta this is equals to 1, and that is called your Barkhausen criterion. When this is equals to 1, then you are going to get the sustained periodic oscillation. Okay. Now let's see what are the different types of oscillators. So we have RC oscillator, LC oscillator, and then crystal oscillator. These three are your sinusoidal oscillator. Its output is sinusoidal, and then you have relaxation oscillator, which is a non-sinusoidal oscillator, and then you have a 555 timer. So we will be discussing some of the oscillators in the next coming lectures. And this is now for today. Thank you so much for watching.